It is my great pleasure to welcome you to the world of learning new concepts and current trends, so let's start. Have you ever tried to cook in a kitchen where everything's just tossed into one giant drawer? Spices are mixed with forks, pots are jumbled up with plates. It's a total nightmare, right? You can't find anything, you wind up grabbing the wrong stuff, and cleanup is just impossible. Well, an unorganized database is exactly like that messy kitchen. Today, we're going to clean it up. We're going to take a simple pizza shop's data and transform it from a chaotic mess into a clean, efficient masterpiece. And we'll do it using a process called normalization. We'll go step by step from total chaos to perfect order. Let's see how we get it done. So here's our game plan for today. We're going to start by staring right into the chaos of our one big messy table. That's what's called the unnormalized form. Then we'll do 3 rounds of tidying up, getting to first, second, and finally third normal form. Each step is going to fix a very specific kind of mess until we're left with this beautiful, clean, and logical design. All right, let's get our hands dirty. Okay, let's jump right into section 1, the one messy table. Before we can start organizing anything, we really have to understand the mess we're in. This is our before picture, that chaotic kitchen drawer where everything has just been tossed in together. To make this super real, just picture a busy Friday night at our pizza shop. A waiter takes an order over the phone and just scribbles everything down on one single notepad. John Smith, his address, his phone number, the 2 pizzas he wants, and the driver who's going to deliver it. Now, for one single order, that might seem okay. But what happens when you've got 100 orders like that? You're left with this giant, unsearchable stack of messy notes. It's a total recipe for disaster. Okay, so let's translate that messy paper note into a database table. This right here is what we call unnormalized form, or UNF for short. Now, take a really close look at that pizza details column for order 101. See how we've stuffed 2 totally different things, a pepperoni pizza and a veggie pizza, into one single cell? Now, a person can read that, but for a database, this is an absolute nightmare. It can't easily search for all pepperoni pizzas or count how many veggie pizzas we sold. This jumble of data in one cell is called a repeating group, and that is our first big problem to solve. So how in the world do we fix this? Well, the process is called normalization, and you can think of it exactly like it says here. It's the formal process of tidying up our data. We're going to break down this one giant table into several smaller, much better organized ones, and we'll put each piece of information in its own correct home. The whole goal here is to get rid of that duplication and prevent all sorts of nasty problems later on. But hold on, before we start cleaning, let's really get why this is such a mess. You might be looking at this table and thinking, it's not that bad. I can read it. So what are the actual real-world problems with storing our data like this? These problems have a technical name, anomalies, which is just a fancy word for errors that happen because of a bad design. And there are 3 main types. First, the update nightmare. Say John Smith calls to update his address. You have to go find every single past order he's ever made and change it. If you miss just one, you now have conflicting info about where he lives. Second, you've got insertion issues. What if we want to add a new Hawaiian pizza to our menu? Where do we put it in this table? Well, we can't, not until a customer actually orders one, which makes absolutely no sense. And third, the deletion dangers. Look at Sue Jones. She only has one order. If she calls to cancel it and we delete that row, poof! We lose her name, her phone number, and her address completely. All of her customer info is just gone because her order was deleted. This is a super fragile and unreliable way to store your important data. Okay, we've seen the problems. It's a mess. So let's move on to our first big tidy up. Our goal here is to achieve what's called first normal form, or 1NF. This is the first, most fundamental step in cleaning our data house. The rule for first normal form is simple, and it is absolute: no repeating groups. Every single cell in your table has to hold one and only one value. The word for this is atomic. Like an atom, it can't be broken down any further. Remember that pizza details column with 2 pizzas crammed into it? That's a total violation of this rule. It's not atomic. You can easily break it down into 2 separate things. To get to first normal form, we have to fix that. And the process is pretty straightforward. First, we spot a repeating group, which is pizza details. Second, we get rid of it by giving each pizza its own unique row. So John Smith's one order now becomes 2 rows, one for pepperoni and one for veggie. And third, this creates a new little puzzle. Every row in a database table must have a unique identifier, called a primary key. Think of it like a license plate for that row. Before, order ID alone worked just fine. But now, the number 101 shows up twice, so it's not unique anymore. The fix is to create a composite key, which just means we combine 2 or more columns to make a unique ID. In our case, the combination of order ID 101 and pizza name pepperoni is unique, and order ID 101 and pizza name veggie is also unique. Problem solved. And here's what we get. We are now officially in first normal form. Every cell has one single atomic value. But hang on a second, look closely. By solving one problem, we've created a really obvious new one. Just look how many times John Smith's name, address, and phone number are repeated. This is massive data duplication. I mean, imagine if he ordered 10 pizzas. We'd have to type his info 10 times. That is not good. And this brings us right to our next stage of cleaning. The huge amount of duplication we just created is now our main target. We're going to fix it by moving to second normal form, or 2NF. So let's just state the new problem really clearly. In our 1NF table, all the information about an order, the customer, the date, the driver, is copied over and over again for every single item in that order. This is not only inefficient, it brings back our old friend, the update nightmare. If John Smith moves, we still have to change his address in multiple places. We gotta fix this. Okay, the rule for second normal form can sound a bit complicated at first, but the idea behind it is actually pretty simple. It says that every piece of information in the row should be about the entire primary key, not just a piece of it. That plain English version on the slide really says it best. If an attribute depends on only part of the key, it is in the wrong place. Let's break down what that really means for our table. Let's apply that rule to our table. Remember, our primary key is order ID plus pizza name. So ask yourself this, does the customer name depend on both of those things? No, of course not. John Smith's name only depends on the order ID, 101. It has absolutely nothing to do with whether he ordered a pepperoni or a veggie pizza. And the same thing is true for his address, his phone number, the order date, and the driver. All of these fields depend on just a part of the key, the order ID, not the whole key. This is a textbook partial dependency, and it's a giant red flag telling us these columns are in the wrong table. So the solution is to decompose the table. We're going to basically perform surgery. We'll carefully remove the columns that are only partially dependent and give them their own, much more logical home. We'll create brand new tables for that data. Then, to make sure we don't lose the connections, we'll use something called a foreign key. A foreign key in one table is simply the primary key from another table. It acts like a bridge, creating a relationship so we always know which customer belongs to which order. Let's see it in action. So here is our first brand new table, customers. Look how simple and clean this is. Each customer is listed exactly one time, with their own unique customer ID. Now, if John Smith moves, we have only one single place to update his address. That is beautiful. Next, we create an orders table. This one holds information about each order as a whole. It's got the order ID as its primary key, the date, and it links to our new customers table using that customer ID as a foreign key. So we can see that order 101 belongs to customer C1, who we know is John Smith. Now, we've still got the driver's name just sitting here for now. We'll come back to that in a minute. And finally, our original table gets a lot smaller and is now called the order items table. Its only job is to connect orders to pizzas. It tells us that order 101 contained a pepperoni and a veggie pizza. That's it. This whole process of breaking one big table into smaller, more focused ones, that is the heart and soul of normalization. All right, let's move on to the final polish. We've made huge progress, but there's one last kind of subtle problem hiding in our new design. Fixing it will bring us to the gold standard of normalization for most databases, third normal form. So I want you to focus on the orders table for a second. The primary key is order ID. The order date and customer ID are facts directly about that specific order. But what about the driver name? Is Jane Doe a fact about order 101? Well, not really. Jane Doe is a fact about the driver. The order just tells us which driver was assigned. This is a more indirect relationship, and that's our final problem to solve. This problem is called a transitive dependency. It sounds fancy, but it's really just like a chain reaction. Here's how it works in our table. The driver name, Jane Doe, depends on the driver, and the driver who's assigned depends on the order ID. So the order ID determines the driver, which then determines the driver name. Because the driver name doesn't depend directly on the order ID, it's in the wrong place. There's this fantastic quote that perfectly captures the spirit of what we're trying to do here, especially with 3NF. It's a great mantra for database design. Every piece of data in a table that isn't the key should be a fact about the key, the whole key, and only the key. Driver name is a fact about the driver, not a fact about the order, so it doesn't belong here. And the solution, by now, should feel familiar. We decompose. We create a new drivers table. Each driver gets a unique driver ID, and their name is stored here and only here. If Jane ever changes her name, we have just one single place to update it. And here's our final updated orders table. We've replaced the driver's actual name with a driver ID foreign key that just points over to our new drivers table. Now, every single non-key column in this table, order date, customer ID, and driver ID, depends directly on the primary key, order ID. This table's clean, it's efficient, and it's fully in third normal form. So after all that cleaning, separating, and organizing, let's just step back for a second and admire the final masterpiece. What did we actually accomplish? This right here is the payoff. We started with one giant, fragile table that was just filled with duplication and potential errors. We ended with this elegant system of interconnected tables: customers, drivers, orders, and order items. And to be totally complete, we'd probably do the same thing for our pizzas, creating a pizzas table with their names and prices. The point is, each individual piece of data, a customer's address, a driver's name, a pizza's price, now has one single logical home. So why does all this matter so much? First, it massively reduces redundancy. Storing facts only once saves space, and way more importantly, it makes updates simple and reliable. Second, it improves what we call data integrity. Those foreign key links mean you can't create an order for a customer who doesn't exist, or delete a driver who still has deliveries assigned. The system actually enforces its own rules. And third, it dramatically increases flexibility. Want to add a new driver? Just add one row to the drivers table. It doesn't disrupt anything else. The system is no longer fragile, it's robust, and it's ready to grow. We started with a messy kitchen, and we ended with a perfectly organized pantry where everything has its own specific place. We took a simple pizza shop and applied the principles of normalization to make its data reliable and efficient. So I'll just leave you with this question. Think about the data you work with every day. Maybe it's a chaotic spreadsheet, a confusing contact list, a project plan. What messy data in your world could be transformed from a total mess into a masterpiece using these very same principles?